All right, Ashwin, you can give me 1 second.
Okay.
Okay, all right, Ashwin, you get started now, and we will hopefully have others trickling in slowly.
Oh, okay. Yeah. So today I'll be presenting the progress on my research on and continuing on from my last presentation. And my topic is on the system identification of an MMG ship maneuvering model using support vector regression.
Can you go into presentation mode?
I am in presentation mode.
Okay, then you have to share your entire screen. Otherwise, we don't see your presentation mode. We only see your regular presentation.
I'll just reshare. What about now?
We see your presentation. Go into presentation mode.
Oh, okay.
No, you have to share your screen, not window.
Okay, okay, okay. What about now?
Yes, it's looking good.
Okay. Okay, so I'll be continuing on from my previous presentation and explaining the new progress made on my research on the system identification of an MMG ship maneuvering model using support vector regression. As a recap, let's go through what I had done in the last presentation. So in my last presentation, I had defined the MMG maneuvering model, and my task was to recreate two maneuvers, the turning circle maneuver and the zigzag maneuver, by defining the mathematical model and trying to generate from it these two maneuvers. And the goal of this was to get the data from these two maneuvers so that I can recreate the hydrodynamic derivatives using support vector regression. So as you can see here, this was my last plot, and there were some problems with the plot, so these were first corrected, and now I actually have the corrected plots here. As you can see, the port and starboard turning circle maneuvers are plotted, and similarly, I have also plotted the zigzag maneuver, corrected zigzag maneuvers for the KCS ship, which I am using as a reference. So now my next task would be to, once I have the corrected trajectories and these from these two maneuvers, I can gather data from these, and I can predict back the hydrodynamic derivatives that were originally used to recreate this maneuvers by using support vector regression, which is my final goal. So let us look at how the support vector regression is set up initially. As you can see, this equation gives is the equations of motion for the 3 degrees of freedom, surge, sway, and yaw. As you can see, u, small v, small u, small v, and r represents the velocities in the x, y, and this is the rotation about z axis, your directions. And correspondingly, the x, capital X, Y, Z here gives the forces and moments acting on the ship. Now, you can see the different types of forces acting on the ship as represented here. Capital X is...
1 second here. What is delta U and delta X? So why you have the delta here?
Delta represents the small increment
Yeah,
because I'm taking discrete values, discrete points.
no, you're taking discrete points, but you're still you're solving the equations of motion, right?
Yes, I'm
It
solving the
is,
equation.
it is not incremental acceleration that will get multiplied by the mass. It should be the full acceleration, isn't it?
Yes, these are the full accelerations, actually.
So then you should not call them delta.
Okay.
I mean, I didn't
So in
see
one
you.
of the abstract papers, it was they put delta. I wasn't sure why. So I just copied it like that.
No, but then in your equation of motion, you're saying x prime, y prime, and n prime are these. But then you're using delta x prime and delta y prime and delta z prime in your forces.
Yes.
Something's not sitting right.
Yeah. So you can ignore these deltas for now. It's actually supposed to be x, y prime, z prime, capital X prime, capital Y prime, capital Z prime, and u dot, v dot, and r dot. Just
Correct.
looking at the equations of motion, these are the equations of motion. And for now, the different we can see the different forces and moments that are contributing to this, which is the H, capital H stands for the hydrodynamic force, capital R is the rudder force, capital C is the Coriolis force, and capital P is the propulsion force given by the propeller. So only XP will have a value because it acts in the body frame X direction, while YP and NP will be zero because the propeller only pushes the ship forward. So once I have the equations of motion, I am collecting the data needed for regression. So this is my vector that I am storing. So from the two maneuvers that I have performed, I will sample U, V, R, and delta for the maneuver, which is and uniformly sampled with a total time of 400 seconds. I'm sampling 800. So that means every 0.5 seconds I take one sample. So this big vector will consist of the data which I'm going to use to recreate the hydrodynamic derivatives. And you can see that the hydrodynamic derivatives will come here in the xh, yh, and nz, which is defined here. So xh, yh, and nh are defined here, and the hydrodynamic derivatives that I'm wishing to estimate from them are given. You can see that they are defined here as x naught, x beta beta, x beta minus my, and xrr, and x beta 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 for the surge motion. Similarly, for the yaw and sway motion, we have the hydrodynamic derivatives such. Similarly, these are the expressions for the rudder force, the propulsion force, and the Coriolis force. As you can see, these derivatives are uh, coded in terms of the drift angle instead of normal u, v, and r. They are in the MMG model. You use the drift angle to parameterize the hydrodynamic derivatives and are given as such. So let us look at how we can restructure the equations of motion so that it can be used as a regression. We can frame it as a regression problem. So these are the equations of motion that I had written earlier. I am just going to expand all the terms consisting that were here that are written here. I will expand these all terms and write them all out like so. Now I will just keep all the hydrodynamic terms to one side, xh terms to one side, and uh, like restructure this as such. If I expand everything, it will look like this. As you can see in these equations, the hydrodynamic terms, the dependent hydrodynamics terms, the derivative terms are on the right hand side, and everything else is kept on the left hand side. Now I will rewrite this right hand side as a matrix by defining this capital X here like so, which consists of the hydrodynamic derivative terms and these non-dimensional state vectors, which I named A, B, C, as like so. So if I do X transpose A, I will get this term. You can see it's just a direct dot product. X naught into U square will give you the first term. X beta beta into beta square will give the second term. So
1 second, Ashwin. Why do you have a 0 at the end?
this is just simply put to make it even. Actually, there is only 5 terms here. There are 6 terms here, and here.
No, but does it
It doesn't
require?
affect it. It's not required. It doesn't affect it any other way because X, Y, and N are being regressed separately.
No,
They are
but
not being regressed together.
yeah, they're not being done together, right? So
Yeah,
in
yeah.
reality,
It doesn't matter.
so in your actual case, the X is only 5 hydrodynamic derivatives that you're trying to predict.
Yes, yes.
So by
In,
giving, no, but you're not passing an input with 0, are you? No.
it's not needed at all.
Yes, it's not needed, right?
Yeah.
Maybe we will be explicit on that. Let's not put it, because this suggests that you're adding an extra input in which you're passing 0. And
Yeah. I just wrote 0 to make it look even. Actually, I'm just predicting 5 derivatives.
yeah, okay. Maybe next time we can avoid it.
Yeah, yeah. So just to keep them consistent, the X transpose A consistent, I just added 0 here. Doesn't matter. Any other questions? Yeah, okay. So continuing on, you can see that once I have rewritten these in terms of capital X, Y, and N and capital A, B, C, I can write this right-hand side as a matrix equation wherein this transpose times ABC will give this left-hand side. So that is what I'm writing here. So this is the final regression equation. All my hydrodynamic derivatives are in X, Y, and N, which I have to predict. And I know A, B, C, and this right-hand side because I already have the manuring data. From the manuring data, I can calculate all these terms, this term and the ABC terms. As you can see, if I have U beta R for each dimension, I can calculate U square, beta R, and so on. Similarly, I have ABC, and on the right-hand side, I'm using the Euler forward chain to calculate the accelerations because I'm not storing the acceleration. I'll have to calculate it using the time interval by subtracting consecutive terms from the search way and your velocities. I will take the velocities and calculate the accelerations using the Euler forward scheme. So I have the accelerations. I know everything else has some constants or calculable variables using the equations above. So I have the regression equation Ax equal to b. Similar here, Ax transpose equal to b something, by transpose equal to something, Cn transpose equal to something. So now,
so we have everything on the right hand side is known, and we know A, B, and C.
yeah, now we just need to so in the regression equation we just need to figure out what x, y, n is by regressing through them.
Okay.
Yeah, someone was asking something.
Any other questions?
Ashwin, it is the
Yeah,
delta u dot or simply the u dot?
It's not delta. You can ignore the delta.
Okay.
all right. Any other questions? Now is the time to ask.
It's just a simple regression problem after this because we have already framed everything. We just need to get x, y, and n from this. And we have some data points which give what a and a is and what this part is.
Okay, you move ahead.
Okay. So in support vector regression, so initially we had a line, right? So we need to figure out what this line is in 2 dimensions. If you go from this high dimensional space to just a 2-dimensional space, and just assume that this x transpose only has 2 variables, it's just simply a line. That is what this is. Y is equal to wx plus b, and we have a lot of data points, and we just need to fit this line using some regression. Now, what support vector regression does is, instead of a normal regression which uses squared error loss, this uses a weighted norm loss, like so. So the loss is defined as W square, which is this W square, and this W corresponds to the previous hydrodynamic derivative square, norm square. So, and which is subjected to some constraints. And so these constraints are necessary because not all the points will be perfectly separable. So we need to provide some slack and an epsilon value in which to draw a regression line. So
Okay. So my understanding is they are trying to minimize the hydrodynamic derivatives, correct?
yes, and this comes from how support vector regression is defined. Support vector regression is a maximum margin classifier. So what you are trying to do is maximize the margin between the closest data point and the line, as you can see here. And if you were to write out the equations, you'll see that the maximum margin would be directly proportional to 1 by W norm. So if you want to maximize 1 by W norm, you have to minimize W square. So that is how you get this.
Okay, did everybody follow that? That's an important piece of information he just talked about.
Can you explain that again? I didn't understand.
Okay, so let's say you have a data point here and a line here, Wx equal to B line. This line is y is equal to Wx plus B. And you have one data point here. So, and what support vector regression does, and support vector machines essentially does is try to maximize this distance between the closest data point and the line. So if you were to maximize this with respect to all the data points, yeah, this perpendicular line. And if you were to write out the equation, you will find out that this perpendicular line is directly proportional to 1 by the norm of the W. So that means maximizing, so maximizing 1 by W norm means minimizing W square. Did you get that one?
Sorry, I still didn't get that. Can you explain it again?
Okay.
Okay.
What he's trying to tell is, okay, support vector regression is kind of built on top of what we call as a support vector machine, which is essentially a classifier. So you have a bunch of points, you want to separate them into two parts. You want to say one part is label 1 and the other part is say label 0. Okay?
Okay.
Now you want to find a line.
Line. In 2D case, it would be a line like this.
Right? Or if it is in a higher dimensional case, it will be a plane or what we call as a hyperplane, which will separate these points and saying that if anything lies above that plane, it's classified one way. If anything lies below that, it's classified the other way.
Yes, sir. Yes.
Okay. What he's saying is, in this methodology, in this algorithm, you will try to maximize the distance between the point which is closest to the hyperplanes on either side. You want to maximize the distance.
See, across all these points, if you were to maximize the distance, you'll get the optimal plane right in between, right? That's why support vector machines are called maximization. I mean, maximization machine.
You can imagine it like this. Suppose he tilts the line towards the bottom slightly. Okay, the right side of the line, he tilts it to the bottom. What will happen? The points which are there in the very end, on the right side, which is at the very end, it will now become closer to the line, isn't it?
Yes, sir. Yes.
Right? But he wants to find a plane such that the distance between the closest point to the plane and the nearest data point is maximized.
Okay, sir. Okay. Okay.
Got it?
Yes, sir. Yes.
Okay.
So
Very
that
good.
is how you get this initial objective function.
No, but a very good question. You see, that is very important to understand. Good question, Aditya.
So this is the non-slack version. This is what you would call a hard margin because they are perfectly separable. You can see, let's say the stars on this side are one color and the stars on this side are another color. In this case, the points are perfectly separable. But say one of the stars here are not belong to type 1 but type 2 instead belong to this category. In that case, you would want to draw what is called a soft margin, which doesn't classify all the points exactly, but there is some margin between them, so that there is some slack in the line, or the hyperplane drawn, such that most of the data points are perfectly separated. So that is where this part comes in, and we can control this parameter through a parameter called C by defining how hard you want the margin to be. You can give a very high value to C or a very low value to C, depending upon how fine you want the margin or how hard you want the margin to be. And these are defined by using something called slack variables, which I will not get into too much.
Okay, so here they are particular to each data point, isn't it?
Yes.
So for each data point, you're kind of choosing a weight that how important is it that my classifier should classify that point. In this case, regress that point correctly.
Yeah, you can see that in the plus in this, that y is equal to wh plus b less than or equal to epsilon plus some slack. The slack is there so that you can modify it, so that you can account for irregular stuff on either side of the hyperplane.
So
And depending upon how much, yeah, okay.
So for more important points, you want that slack to be less.
Yes, yes.
Right? Now, what is the difference between the slack and its slack star? You have one variable chi and the other one is chi star.
Yeah, one is on top, the other is on the bottom.
Correct. So one is trying to specify the points on one side of it, the other is trying to specify the points on the other side of it. So you can have different margins on either side.
Yeah, you can see that is defined by this. This restriction ensures that.
Okay, did everybody get that?
And you'll see that the whole support vector regression is a optimization problem, and it's a constraint optimization problem where these three are the constraints. What happens after this is you write it in a more using a dual. You'll write the constraints in a more simpler problem and try to solve the dual problem, which is much more easier for solvers to solve. Exactly. So basically, we are trying to regress this W from data points fx and whatever we have here, which is exactly what I have defined here. This is the basics of a support vector regression solver. So continuing on from this, these are the regress derivatives that I have got. You can see the derivatives, the surge derivatives here, sway here, and the yaw derivatives here, and you can see the pattern. Like most of some of the derivatives are matching almost, while the others are not exactly matching. And you can see that the first order derivatives are matching, while the higher order derivatives are not matching. And this is mainly due to a problem called parameter drift. And during parameter drift, the higher order derivatives become non-unique, which means there would be more than one solution due to the regression problem. So in that case, this is one of the major problems that I'm currently facing, and that any system identification challenge will have to try to solve. So you can see that even with these derivatives that I have, even with the wrong derivatives that I have regressed, I'm getting pretty good results. The blue one is the original one with the original derivatives, while the orange one is the SVM one with the wrong derivatives. So this is what I meant by having more than one solution. So to get the correct solution, I'll need to employ some other techniques, and these techniques are called, so during parameter drift, solution of the regression problem becomes non-unique. So that is a major problem. So alleviating parametric drift, different methods are proposed, and these are the ones that I'm currently trying out. One is called batching, where I use more than one maneuver and make those and add up them to make one new matrix. Another method is using Gaussian noise, addition of some noise. And there is also something called difference method, where I take consecutive differences between the data points to introduce more nonlinearity. And this is one more technique that I came up with, which is randomizing the input data, which also seems to be working, but not that good.
What is the third one? Come again?
Difference method.
So what are we doing in the difference method?
We just take consecutive difference between the matrices, rows. ABC matrix, we take differences. If you have A matrix, you just do x1 minus x0, then x2 minus x3, and store them.
No, I didn't understand. So in your X matrix, you're
No,
taking.
A matrix. Okay. A matrix is made up of rows, right? You just take the difference of the rows and store them, consecutive differences.
And then you multiply that by X matrix?
Yeah, and like subtracting individual points in A doesn't affect because all of them they are linear. So you have to the methods you can currently use are like just linear transformations to introduce more nonlinearity.
No. Okay, maybe back up here a little bit. Okay, so if considering that you have a data from.
So batching is like A1 plus A2, right? You have two different maneuvers and you add the two
Let me
maneuvers.
ask my question first before
Yeah,
you
okay.
answer it. Okay, so if you have say 800 data points times
Yes.
of 800 data points,
Yes.
okay, and let's say that you're looking at a single maneuver which is coming from a turning circle maneuver.
Yes.
Then what will be the sizes of A, X, and your right hand side?
Okay. You have in X we had 5 derivatives, right?
Mm-hmm.
So this is a column vector of 5. This will be 800 cross 5.
It will be 800 cross 5.
Yes.
Okay. Now
And you can now make a new A matrix. That is, you modify this A matrix to introduce some more nonlinearity. And that,
okay. So now
and for that,
tell me with respect to a difference method, how would you modify this 800 cross 5 matrix?
I'll just take one row and subtract it from the next. I'll take the next one row, subtract it.
Okay.
Just subtracting consecutive rows.
Okay, consecutive differences of time step. On the time step, it is the difference.
Yes, on the time step, it is the difference.
Okay, all right. And
here also, I'll do the same thing.
You'll do the same thing. Why will that introduce nonlinearity?
Because they are two different data points, and by subtracting them, it's supposed to induce something.
No,
but I didn't. This is what the difference method does, but I didn't find it actually working too well for me, especially for the search motions.
No. I'm curious now to find out, understand, if you take a difference from one time step to the next time step, why would it be yielding better?
So when you're regressing, that one time step you're taking will have information from the time step from the next one and the current one.
Yeah, okay, you're taking information, but I am not still seeing why it should improve. There should be a logic to why it should improve, right?
Basically, what you're trying to do is trying to make this A transpose X some kind of plane or something as complicated as possible, so that you can put a high value of C and fit it perfectly to get rid of the multicollinearity.
No, high value of C. Why did C come into picture?
Yeah. So you want to use a high value C that you have so that you get a perfect fit, right?
No, I think can you go back in your slide? I think you have multiple definitions of C, which is causing some confusion. There is
the C I'm meaning about is this C, this C, so that we have a really hard margin. So instead of just this one simple line, if I were to make this as complicated Lishwash and put a really high value of C, I'll get a better chance of fitting it perfectly and getting the correct derivatives out. rather than the multi-collinear round derivatives.
Yeah, the moment you're saying you're trying to find a high value of C, you're giving more importance to the data rather than to the finding a regularization. Okay.
Yeah.
Okay, I'm trying to understand this. Okay. All right. So if you put by taking
So
a
that,
difference,
yeah, you're introducing further non-linearity, meaning more complexity into this line. That would be what is happening.
by taking a difference, how? It is
Okay,
still the same derivatives, right? Can you go back to the case, the slide where you were talking about this, the one slide which you were seeing previously?
which one?
No, no, no. Can you go back, one more? One more? Yeah, right here.
Yeah.
This A matrix, you're saying that you're going to take a difference between the rows.
Yes. These are one of the methods proposed. So I'm not sure how they propose this, but at least for the people who have tried it worked for them.
No, I'm just wondering that if you take a difference of the row matrices A, it will change the, it will not change the rank of A. It will still be, but you're kind of avoiding probably some common factors. So what is the difference incrementally is what you're looking at.
Yeah, but it wouldn't work for if your later readings are like constant. In that case, it just becomes zero, right? And you're
Yeah.
not doing anything helpful.
For example, let's say I'm looking at a turning circle maneuver. That's
Yeah,
what
yeah.
is the
So
point.
that is what is happening. That is what is happening to
R
the
will be
turning circle.
zero. Like
Yeah.
if you take a consecutive difference of R after it has reached steady state, it will be zeros, right?
Yes, yes.
So it will actually not make an impact in
Hmm.
getting
So like,
XRR any better.
yeah. So from what I have tried, the best one is still batching. And Gaussian noise, I'm not sure if it's doing much. Batching seems to be working, but
Patching will
not as
work.
well.
That does make sense to me, because let's say that you have a turning circle maneuver in which R is not so important, but beta is more important. But let's say you have a zigzag maneuver, let's say where beta is less important and R is more important, or playing
Yeah, yeah.
significantly to the dynamics. So if you add the two together, you get the best of both the worlds, that you also are able to predict beta well and RL or R also well.
Yes.
Right? So coefficients of beta and coefficients of R start to converge a little better. So batching, I understand. Noise, not so much.
Noise would be just like for more generalization, but I am not sure if it's worth it.
But the difference is something which is interesting actually. It may highlight some ones which we were not able to predict previously very well, but some others it may perform very badly.
Yeah, that is what is happening to the search, especially in the turning circle, because everything is getting cancelled out.
That's what is happening. You're observing that in the results.
Yes, yes. For search, the difference method is not working, especially in the turning circle, because everything's a constant after some time.
Correct. So everything will steady state out. So therefore
Yeah.
there will be nothing to, it'll all become zeros.
Yes.
Okay. All right. So, but whereas in a zigzag maneuver, it might make some sense.
So what I tried is, that in the turning circle, it just after some time everything goes to steady state, right? So I
Correct.
tried reversing it and adding it to the A, so that in the beginning there will be some disturbances due to the initial thing. Also in the end, also there will be a mimic of this disturbances.
No, I didn't follow. What is reversing?
I will reverse the values of the rows of A matrix and add it onto the A matrix.
You reverse the values of A.
Reverse the rows of A.
Ah.
So we have A0 to A800. A800 I will add it to A0. A799 will add it to 2. So that I will get a symmetric graph, something like this, symmetric.
Yeah,
And
but
there will be differences on both sides, and the machine will have to fit both the sides. That seems to be also working, but not that well.
yeah, because there is some limited information. You can't get more information out of it as
Yes.
compared to batching multiple maneuvers together, right?
Yes, yes. So as the more manuals you have, the better will be the
Correct.
regressive images. And I don't think the turning circle is the best maneuver
No,
to actually try this on.
we discussed about something else, right? The
Yeah.
spiral maneuver. Have
Yes.
you given it some try yet or not
No,
yet?
I haven't tried spiral maneuver yet. I'm still trying to optimize the other two. Then I thought I would, if that doesn't work at all, I'd try the spiral maneuver.
Okay, all right. I think the spiral might have some advantage because you're continuously dynamically changing the
Yeah.
derivatives and you're making the turn sharper and sharper. Or
So what is this ABC matrices? I need them to be completely, like, there should be some significant change between the rows throughout to get some good values.
yeah, that will
Yeah.
happen
So
only if the maneuver is very dynamic in nature.
yeah. So in case of turning circle, these are becoming constant after time.
That's true. That's true. They will become constant and they will
Yeah.
not yield anything in a difference method. Okay, all right.
So that is where I am at currently.
Okay. So even though we are getting the right
Yeah,
turn,
even though it's exactly, you can see how good they're matching, but it probably won't match for other manuals.
okay, sounds good. All right. Any other questions from others? Come on, there cannot be no questions. Even if you did not understand something, ask him.
Can you go to the support vector regression, that slide, that line? Yeah, like in the classification case, we have this this margin, the soft margin that you said, that will be limiting the misclassifications distance from the hard margin, right?
Yes. So soft
In
margin, what you're trying to achieve by a soft margin is necessary when you have when you can't actually get a really good hard margin because of the distribution of the data. The data can
like,
be linearly separable or non-linearly separable. In
hmm,
non-linearly separable cases, you would need a soft margin.
okay.
Yeah.
No, does it have anything to do with linearly or non-linearly? As long as it is not separable, you will need a soft margin.
Yeah. Not separable,
Like
you need a soft margin.
these
Yes.
the uh, points from one class are getting mixed into the other class. Is that what is happening?
That is what is happening.
Okay.
If you were to put a hard margin on that, it will try to include that point also, which will be
Hmm.
unnecessary.
It will be like very
Yeah,
weird.
it will go like this or something. If you have a type 2 here, this line will adjust to it and try to include that point also.
And then later steps that you are trying to complicate that, you said, then what will that be doing?
Which exact step do you
In
want me to?
later on, you the methods, that additional methods that you are exploring, that will make changes C, capital C, that you said.
Where you're trying to address the parameter drift.
Parameter.
No, I'm not doing anything to the support vector regression part when trying to minimize parameter drift.
You said
No,
something that you will be making you will be making this complicated.
no. I was like the further after this step. If this is the definition of the regression problem, and this is a optimization problem right now. In further steps, when actually trying to solve it, when you are trying to code the solver, you'll turn this optimization problem into a dual problem using something called a TTK, Karush-Hunter conditions, where you turn this primal problem into a dual problem and you simplify these inequalities into simpler inequalities. And that is actually what is programmed to be solved instead of this actual equations. It's just inner workings of how support vector regression works. It's not related to the batching of the parameter drift alleviation techniques.
Okay, Vallabh, was that clear?
Like I will have to read up on
Yeah, the
support vector
support.
machines first.
Yeah, the
Okay.
support vector. You just have to just read upon it if
One
you want to
second.
understand it more.
Okay, give me a second here, Ashwin. All right, so the primary idea is what he's saying is this problem which is being specified as an optimization problem, you can convert that into a different sort of a problem, and solving the different problem, which is called as the dual of the problem, is easier than solving this problem.
Yes,
So
mainly because these inequalities become much simpler.
okay, so primarily the idea is that you're solving the same problem, but it's formatted in a different way. You can think about it.
Yeah, using simpler inequalities.
Is that making sense, Vallam?
Yes, yes, sir.
So that is a part of a process which any optimizer will be doing when looking at such classification or regression problems.
Yes, that is how you KKT conditions is how you like solve these inequalities, inequality constraint problems. This is already a convex optimization problem. You convert it into another convex optimization problem with lesser, much more by introducing some more variables actually.
And that is already being inbuilt, taken care of by your solvers.
Yes,
You are
yes,
not
that is.
programming or playing with that.
No,
Correct?
I'm not doing anything
Yeah.
with that. If you want to do anything, it's just the best thing we can do to alleviate parameter drift is to use a better kernel rather than the linear one. But in that case, you can't get back this W perfectly without some actually going into this.
Yeah, then it becomes complex actually because you don't know which feature vector it is getting mapped to.
Yes.
Here you're doing a linear regression. So for your case, phi of xj is xj, isn't it?
Yes.
Okay. Any other questions, comments? Come on, guys. I'm seeing the participation kind of decline here. Why?
Ashwin,
Yes.
in the constraints, why we are not considering that minus epsilon or its error? Why we are not taking the more than or equal to minus error?
You have this. This is the plus error. This is the minus error.
No, no. What he's asking is, why should the
Yes.
constraint be limited to epsilon? What is that constraint exactly doing?
Okay. So this constraint is another variable which determines how big your margin wants to be. So if your data points are really far apart, you can put your margin as a very big, or depending upon how your data points look like, you have this is a tunable parameter. It's basically takes care of big discrepancies in your data points. If some of your data is concentrated closely or how far away, if your data is concentrated really far apart, you can define the margin to be as big or as small as you want by tuning this epsilon.
No, I think the question more is like, so what happens to the data points which are outside this margin?
Like I think the epsilon is for defining the hard and the soft margin, the width of the soft margin. you are how many points you want to include inside the margin and how much slack you have to give them.
Correct. So whichever is outside the epsilon anyway is getting classified properly or is getting regressed, right? Here,
Yes.
I do have a question though, like when you say that yi minus w times xi minus b is less than equal to epsilon, here we are trying to put a linear line through it, isn't it?
Hmm.
Okay, and that's what you're trying to say. If it's a nonlinear line, if I take a kernel function, then the problem is that I don't know what those weights now represent. I have to go digging into the,
Yes. So this line itself becomes different,
yes,
and
the
and
line.
and these will be lost.
Yeah, the fact that W represents hydrodynamic derivatives will be lost.
Yes.
It
And you
won't.
can't get them back because it's being non-linearly multiplied.
Correct. Okay, all right. Any other thoughts? Yeah, can I see this result
Like,
slide? I was
so
about to ask.
how much more improvement should we look to see? Like all of them need to match perfectly, right?
No, what I feel here is that the problem lies with the fact that, say, for example, YBBB, okay, which is representing the third derivative of y with respect to beta.
Yes.
It is not playing a role in either your turning circle maneuver or the what you call zigzag maneuver, possibly. Okay, if you look at very sharp turns, like
Yeah.
sharp turns which are going one way and then suddenly you're shifting another way,
Mm.
maybe then in those maneuvers these might become important, that they play a significant effect on the dynamics, that when you use those maneuvers in your support vector regression you can get a better estimate of those values.
Yeah. So we'll need maneuvers like that.
Correct. So we need to
Also for
identify
the Y,
maneuvers.
also for this YRR, you can see how small they are.
Yes, they are small.
And for these time to get excited, you need a sufficiently high value of R.
Yes, which means that you might actually need, yeah, so it's a question of two things actually. One thing is whether they are important or not becomes one way of looking at it, and the
Yes.
other thing to think is if they are important you can predict them. So question is, are how do you change between which are important but not predictable from your maneuvers? That is where the scope for improvement lies. Right? If there is something which is not important, if a derivative is not making much of a dent in the dynamics ever in any sort of maneuvers, then to predict that coefficient is impossible.
Okay.
Right? Only those maneuvers where these coefficients make a significant contribution to the
Like,
dynamics,
yeah,
then
yeah.
only we can try to predict them.
So we can't add more terms. We can only get rid of terms right now.
No, it's not necessary that that's the way. There may be some terms which are not included here, which may be important also.
Now, like only way, like you have first order here, you have third order here, next order here is 5, next order here is 6.
Yes.
So you can only go up, and they won't be.
Not necessarily though. Becomes tricky actually.
Yeah, in 6 order 6, R power 6 will be too small to even register from the regression.
No, I'm not talking about R power 6. Probably the cross terms. B power 5 times R may still be
Yeah.
important.
Those may still be, yeah.
Right, you will not know that ahead of time.
Yeah. So in that case, we need to make the correlation matrix and figure out, eliminate things from there and figure out which ones are more important.
Yeah. All right, sounds good.
Yeah.
Okay, we'll stop recording right now.